Let's take a look at the force of gravity as we lift an object from some lower height to some higher height. In our first example, we'll lift the object straight up from height A to height B. What's the work done by gravity? As the object goes up, the work done by gravity for case 1 is just the force times the distance times the cosine of theta, and theta is 180 degrees. The object is moving up and the force of gravity is pulling down. So we get negative mgh, where this is the height h. Now this time, let's take a slightly different path. Let's take our object from height A, and we're going to move it up and then turn around and come back and end up at the same height at B as we did last time. So let's take a look at this. We'll call this extra distance here y. So this is example 2. So our work done in example 2 is going to be the work done for this first part. I'll color code it, the blue part. And that's the same as the work done for path 1. That's just path 1 minus mgh plus the work done for this red part here, where we're going up an extra y distance. So that's going to be minus mgy minus, because the object is going up and the force of gravity is down. And then we have one more leg we have to draw in there. I'll use gray. And that's going to be plus mgy, because the force of gravity and the displacement are in the same direction. So we get a cosine 0 degrees, we get plus. And these cancel out, and we get the same amount of work done as we got in path 1. Let's take a look at another path. We'll call this path 3. And for path 3, we're going to move in this direction, and then we're going to go up, and then we're going to move over here. And we're going to end up right above where we started. And the work done along path 3 is going to be the work done on this side, which is just 0, because the force of gravity is down and the displacement is to the right, and they form a 90-degree angle. So we get an mg times the distance times the cosine 90 degrees. We get 0 work done. Then we have our vertical, which is the same as it was in path 1. We're just finding the work done, moving from our initial point to our final point for 3 different cases here. And then the last little part also produces no work. So in situation 1, we went from an initial place to a final place just by lifting it straight up. In situation 2, we lifted it up past where we wanted to go, and then we lifted it back down. We brought it back down. And in case 3, we're moving this way, and then up, and then that way. We're taking this roundabout path to get from our starting point to our ending point. But in all 3 cases, we started and ended in the same situation. We just took different paths getting from one to the other. And the interesting thing here is that the work done is the same for every path we took. These are very special paths where it's easy to calculate the work done. But I could pick any path between those 2 points, and the work done would be the same. And this is a special kind of force. The force of gravity is a special kind of force. We say it's a conservative force. When a force is conservative, the work done between 2 points only depends on the endpoints. It does not depend on the path you took to get from one place to the other. The force of gravity is the first conservative force we're learning about. But there's another one we know about also, and that's the spring force. When we have an object on a spring, and we're moving it from some initial to some final location, it doesn't matter how we move it. We could move it along the red path, a straight line path, going from its initial to its final location. Just stretch it out, and the work done by that spring would be exactly the same as if we moved it on this path, way out, and then brought it back. And the work done would be exactly the same as if we moved on this green path, if we pushed it in and then came out. The work done for all 3 of those paths would be the same. This is also a conservative force. Those are 2 conservative forces that we learn about in Physics 4a. In Physics 4b, you learn about a 3rd conservative force. The electric force is also a conservative force. Let's take a look at something that's not a conservative force: friction. So if we look down from above at the floor of our room, and we have a box sitting on the floor of our room, and we want to move it from point A to point B, we can do that a number of ways, right? We can just push it straight across from A to B, take path 1 here, and if this is a distance D, capital D, between those 2 points, the work done by friction is going to be the force of friction times the distance times the cosine of the angle we get when we put their tails together. And the force of friction is mu times the normal force. And the normal force for a box sitting on the floor is just mg, the weight of the box. So now we see we've got the work done by friction taking this red path here. We'll call that path 1. But what if I took this path? I went this way a distance lowercase d, and then I went along d, and then back this way lowercase d. I could have taken that long convoluted path over, and we'll call that path 2. And the work done for path 2 is going to be the work done for the first part. I'll call it A, B, C. This is going to be the work done for part A plus the work done for part B plus the work done for part C. We'll add them up. And what do we get? For A, it's going to be the force of friction times the distance times the cosine of 180. Because as we push the box in that direction, the force of friction is in the opposite direction. We get a cosine of 180 degrees. And then along the path B, the same thing is true. We're pushing the box this way. The force of kinetic friction is the opposite direction. We get a cosine 180. The work done is negative. And then along this last path, the same thing is true. We get that cosine of 180. along part C. And we add all this up, and we don't get the same as we got last time. We get a much bigger work done by friction. This is a non-conservative force. Conservative forces, the work done for every path between 2 points is the same. Non-conservative force, the work done depends on the path taken between the 2 points. Why do we care about conservative forces? Because every time we see a conservative force, we come up with a potential energy term. In general, the work going from A to B, from an initial to a final location, is just the integral of f dot dx. Now, if it's gravity, we can plug in there we get minus mgy final we're going from some initial state to some final state. The cosine 180 gives us this minus sign, and then the rest of the integral gives us what's in the parentheses. So what we say is that, wait a minute, the work done here just depends on the endpoints, where we started and where we ended. That's the definition of a conservative force. So we say, why don't we let this equal potential energy? We'll define it right here. Define our potential energy, and work is going to be equal to negative delta U. So the work done by gravity is negative the change in gravitational potential energy. And we can do the same thing for our spring. For our spring, we get 1/2 kx squared. And next quarter, you're going to see there's an electric potential energy also. As we learn about new conservative forces, we'll add potential energy terms. We use potential energy to account for exchanges of energy within our system. It's important to define a system when you do a problem. So for a gravity problem, if you include the Earth in your system, you would use gravitational potential energy to account for changes in energy within the system. If you exclude the Earth from your system, then you can't use gravitational potential energy. You have to say some external force reached into your system, that external force being the force of gravity, and it did work on your system. Same with the springs. We'll say the spring is inside of our system, part of our system, then we can account for exchanges of energy with the spring and our mass by using potential energy. If the spring is not in our system, we can't do that.